As GPT grows bigger and requires more computation, we're burning through electricity and dollars, seriously burning through them at a rate of about $1.50 to $2.3 million a day. Users are increasing. But AI is becoming more expensive than people, which is a really paradoxical situation that we're facing right now. So the most crucial thing is that dedicated hardware has become essential. I used to go around saying it's not a luxury but a necessity if you want to survive. Well, that future is here, and now because of GPT, Nvidia's monopoly is starting to crumble.
Hello, I'm Lee Jae-won, a reporter. Today I'm finally joined by someone I've been really hoping to meet. He's Park Sung-hyun, CEO of Rebellions, one of the few AI semiconductor startups in Korea. Nice to meet you, Park.
Nice to meet you. Thank you for inviting me.
I've really wanted to meet you. You must be incredibly busy, right? Your company makes the semiconductors that are the foundation of AI, and with AI services so hot, you're probably swamped. It was tough to get you here, but we'll make this interview worthwhile. First, terms like AI semiconductor, NPU, and AI accelerator seem pretty interchangeable in the media.
What you just said is excellent, because AI accelerator is actually the most accurate term. If we're being specific, it's an AI hardware accelerator. We also use the term AI semiconductor, or NPU, but Google calls theirs TPU, and Grok calls theirs IPU. That's mostly for branding. I was in the US for 11 years, and generally, AI hardware accelerator is the most precise term because an AI semiconductor is basically a specialized chip for computing AI algorithms. The interesting thing is that AI algorithms can actually run on CPUs, and of course they run on GPUs, so it's a subset. A GPU is a subset of a CPU, and what we call an NPU is a subset of a GPU. So anything an NPU can run, a GPU can run, and anything a GPU can run, a CPU can run. That's why the word accelerator is important in this context. It's not about what can our AI chip run, but rather what algorithms can our AI chip accelerate. So AI accelerator is the accurate term. However, semiconductor sounds cool, and with CPU, GPU, NPU, it feels like a PU series. But an NPU, or more precisely an AI accelerator, is designed to handle the unique patterns of AI algorithms like memory access patterns and computation patterns. An AI semiconductor is essentially specialized for these algorithms. GPUs can perform other operations like graphics rendering, which NPUs can't. Think of a GPU as a restaurant with 10 menu items, while an NPU is a restaurant with only 3. But those 3 items are much tastier and at the same time cheaper. It's not just about better performance, it's also about low operating and adoption costs.
So it's a semiconductor that's completely specialized for those tasks. Then where do AI accelerators usually connect and work? Do they connect to the CPU or do they connect to the GPU?
That's right. Things like GPUs and even FPGAs or NPUs like ours are called coprocessors. The main processor is still the CPU, and you can pretty much assume nothing happens without it. What's the difference between a CPU and a GPU and an NPU? A CPU is where the operating system, like Windows or Linux, is ported and runs as the main system. Whether it's a GPU or an NPU, you typically have one CPU with 4 or 8 of these plugged in, so a GPU can't do anything on its own, and neither can an NPU. They're attached as coprocessors to the CPU to help it perform tasks faster and with less power. That's the role they play.
So a CPU always needs to be there, but when you're building a computer, can you have only an NPU without a GPU?
You got it. If you go without a GPU, then you won't be able to play games.
But you could do AI research much faster and more efficiently, right?
Technically, you can do video editing, but it would be much slower than with a GPU. Instead, you'd be doing the video editing with the CPU. Every task and workload runs on the CPU. The coprocessor is just where the CPU offloads workloads. It's like the CPU says, you're better at this than I am, so you handle it. The CPU does all the overall scheduling. It decides, okay, GPU, you handle this, NPU, you handle that, and you other guys do something else. It's all about distributing those workloads. So without a CPU, nothing happens.
It's just like going to a construction site where the foreman is there saying, okay, carpenters, you're up, and then plasterers, you come now. They're distributing the work. It's the same thing.
That's right, but the carpenter actually gets paid more than the foreman. It's a really paradoxical situation where the GPU is more expensive than the CPU.
Okay, for today, I'll just use the term AI semiconductor for AI accelerator. So why did these AI semiconductors emerge, and when did they first appear?
Well, the concept itself existed when I was doing my PhD, so from 2009 to 2014, it has a long and established history. The only difference is what prefix gets added to hardware accelerator. Is it AI or Bitcoin mining? It's about taking a specific algorithm and essentially baking it into hardware, into silicon. NPUs also have generations. Since NPUs have a history spanning over 10 years, they've gone through first, second, and third generations, precisely following those eras. To get a bit technical, AI algorithms evolve, and naturally, as they change, AI semiconductors change to match. Initially, we had CNNs, convolutional neural networks, which were primarily for computer vision tasks. We'd create a semiconductor that was incredibly efficient at calculating CNNs. Then later, there were things like RNNs. RNNs also had to be supported, and CNNs simultaneously, Then there was the need for training, the epochs involved in creating models, and inference, which is serving the trained models. Now, with everyone talking about GPT, it's not just CNNs and RNNs, but also transformers that need to be served. So, as AI has evolved, so have AI semiconductors, going through first-generation inference and second-generation training. Companies like Google and Habana Labs followed the same path. The concept that emerged back then was the AI semiconductor, and you can understand it as AI semiconductors evolving alongside AI itself.
It's similar to Moore's law then. So will NPUs keep developing like this? Will their performance just keep doubling or tripling over time, just like Moore's law?
That's an excellent point. Before GPT came out, the crucial thing for NPUs was flexibility. It was about what algorithms can it run. Because AI algorithms constantly change under the guise of AI. If I was trading at Morgan Stanley and went from using algorithm A to algorithm C, I wouldn't want the semiconductor to only support the old one. So flexibility was key. But now we've pretty much reached a point where this is enough. We're going back to basics, asking why did AI semiconductors even emerge in the first place? They came about for energy efficiency and performance. However, by emphasizing flexibility, NPUs paradoxically started to resemble GPUs, and the gains began to disappear. In the early days when CNs first appeared, the energy efficiency was like 10 times better than GPUs. But by focusing so much on flexibility, even a really well-made NPU today only offers about 3 to 4 times the efficiency. And frankly, 3 to 4 times isn't quite enough. Well, because our software ecosystem still isn't as good as the GPUs, so let's go back to basics. Looking at the original reason AI semiconductors were born, even if it means sacrificing some flexibility, or just running one transformer, or just one GPT, let's get back to basics and aim for around 5 to 10 times better efficiency again. You could say that's the core motivation behind why we started Rebellions.
To briefly summarize, NPUs have been continuously evolving. The key factor until recently was flexibility, right? We tend to think of all AI as the same, but that's not the case. There are diverse algorithms. The crucial point was whether the NPU could run all of them. However, that approach led to a drop in power efficiency, performance per watt, excessive power consumption, and higher costs. So now the trend is shifting towards specializing in specific algorithms. Is that the general direction of this change?
I'd like to make a slight amendment there. So flexibility is still important. It's just that it was emphasized so much that customers started demanding support for algorithms that hadn't even come out yet, what we call future-proofing. Demanding future algorithms that don't even exist yet, that was pushing it too far. The idea is to maintain a certain level of flexibility, but to sacrifice about 10% of that 100% flexibility to achieve more than double-digit energy efficiency gains again. This was the motivation behind the most recent versions from Habana Labs, IBM's Watson, and now Rebellions. The goal is to truly focus on power efficiency while sacrificing only a little bit of flexibility. That's the background.
Okay, I understand. So it's not about completely giving it up, but if you can gain a lot more power efficiency by slightly reducing it, then that's the direction to go in.
It's asymmetrical. If sacrificing a little bit means you can gain this much, then there's a gain that comes from that asymmetry.
In this era of ChatGPT, these transformer-based GPT models are crucial. So in a way, can we say that the emergence of GPT is what caused the shift in the NPU market?
With GPT, the storyline became much easier to craft. When we met with investors before GPT, the fact that it cost so much money was something only technical folks really understood. They knew it was a future that would eventually come. But now, ChatGPT is an immediate reality. Microsoft is experiencing cash burn. And what is cash burn? It's literally burning through dollars. According to some rumors, it's about $1.5 million a day, roughly $1.50 to $2.3 million. If you extrapolate that over a year, it could be close to $1 billion. Users are increasing, and while AI could replace people, it's a truly paradoxical situation where AI is becoming more expensive than humans. And the overall adoption cost is crucial. We call it TCO, or total cost of ownership. For this service, electricity costs are incredibly important. There's the operating cost plus the adoption cost. The adoption cost isn't just about plugging in GPUs. It also means having to redo the data center's electrical infrastructure just to feed those GPUs. As GPU instances increase, they consume so much power that major IDC providers are now directly negotiating with KEPCO to secure electricity. This requires an enormous TCO. So if our startup investment thesis used to be, that'll happen in the future, it's no longer just a future possibility. It's happening right now. That's why companies like Microsoft are feeling the pressure. And while Microsoft is doing incredibly well, teams still believe Google has a chance because Google has successfully developed its TPU in-house. The issue is that if ChatGPT is too expensive, it's like I'm about to head back to Bundang, and if a nice taxi costs about $30, that's fine. But if the taxi fare was $3,000, nobody would take it. Even a billionaire wouldn't use it. That's the kind of feeling we're talking about. Right now, ChatGPT has grown so massive and its computational demands are so huge that from the perspective of someone doing the calculations, you might think they're calculating all that just to give this kind of answer. It's performing an enormous amount of matrix multiplication constantly, and on the back end, they're truly burning through electricity and dollars to keep it running. So the question is this really the right direction? While there are various solutions, the most crucial thing is that dedicated hardware has become essential. I've been saying for the past year that AI semiconductors aren't a luxury just for cool companies like Google. Instead, they're a necessity if you want to survive, something you just have to do to make a living. And now, that future is here.
So a generative AI service ultimately involves AI training and then moving into the inference stage, which is reasoning. To do that, you need immense AI power and a lot of electricity. Therefore, to reduce costs, we need these NPUs or AI hardware accelerators. Is that a fair summary?
NPU companies, the really massive ones in the US, companies worth tens of billions like Sambanova, Graphcore, Grok, and Cerebras, initially all focused on the training market, on creating models. But now, we've entered a market where inference is becoming more important. Teams that are building services by buying APIs from OpenAI to use their models, if things continue as they are, it just benefits AWS and by extension Nvidia on the back end. It becomes a business with no profit left for the service providers. So the idea is to bring that core capability to Korea. Whether it's KT, Nava, or Kakao, each wanting to own it themselves. That's the significance of this full stack approach.
I recently read articles about Stability AI, which operates stable diffusion, buying an additional 10,000 or so Nvidia Aoni 100 series GPUs, and MS also purchased tens of millions of dollars worth of H100S. I now understand that NPUs are incredibly good, but despite that, are people still buying GPUs?
Now, because of ChatGPT, Nvidia's monopoly is starting to crumble. Why was it like that before? While it's about price, it was a somewhat manageable cost. And there are pros and cons. Nvidia is still expensive and power hungry, but since it wasn't a service used by so many people yet, it was tolerable. However, GPUs have grown alongside the AI ecosystem since the early 2000s, so there's a well-established developer ecosystem based on CUDA, a specific CUDA API, and a dedicated library called QDN. There simply wasn't a big enough need to abandon that, especially for developers. Switching to something else on the back end instantly delays the development period. Every developer is constantly battling deadlines. If you keep trying to change things, it requires a strategic decision from the company. Even Google's TPU, which is now at version 7, wasn't widely used in-house until version 3. Management would say, we're building this team, so use it, but GPUs were just easier for everyone. There are some inconveniences, of course, but it really comes down to something else, having to change your habits. If you have CUDA for one system, there's an ecosystem called TVM for the other. NPU companies like ours all contribute to collectively build this TVM ecosystem, and while it's technically usable, it's a bit inconvenient because people aren't used to it.
Basically, CUDA is a development environment created by Nvidia, right? Because they're so used to that, companies are still hesitant to switch to NPUs, and developers might even resist it. I mean, it's not like the money is coming out of their own pockets, so for now, that's how it is.
That's right. The top management sees the rising electricity costs and other issues. Paradoxically, the more technically focused a company is, the slower it is to switch to NPUs. Even in the US, you see this. You'd think very tech-savvy companies would be the first to use these, but it's often national labs where management makes top-down decisions that are adopting NPUs quite broadly in the market right now.
Then Google also has its tensor processing units. Have they adopted them widely by now?
There are rumors that they can't use TPUs because they don't have enough of them, and I understand that's largely true.
Were they using Nvidia before that? So Nvidia really held a strong grip everywhere then?
Because it's convenient. It's not about what's good or bad.
To sum it up, what's the main competitive advantage of an NPU compared to a GPU? Could you briefly explain that?
Right now, it's power efficiency. If a data center spends, say, around $23 million on electricity a month, that could be cut down to about $7.7 million. And it's not just electricity. There are also cooling impacts, and you can cut out the huge price margins that come from Nvidia's monopoly. So adoption costs and operating costs are falling very significantly, and at the same time, the performance is also better for specific algorithms. It's not an OR, it's an AND. It offers both energy efficiency and good performance. That's the pros. The cons are that developers aren't quite used to it yet. They've been comfortable with their current environment for 20 years. That 20-year environment is now slowly changing. No matter how much you talk about self-driving electric cars, some people just won't try them. They'll say, self-driving is dangerous, or how do I charge an EV? Only the hipsters get into them at first, but at some point gasoline cars start feeling clunky. Then, the migration to electric cars happens rapidly. Now, because of ChatGPT, management is also saying the survival of the company depends on this. So the shift will be gradual, but they'll migrate. If they get an order for 100 GPUs, they might say, let's buy 90 GPUs, but for 10, let's try the NPU. Or, let's buy 80, and next year we'll try this. It's the exact same scenario as EV cars. We still won't be able to replace GPUs for video editing, right? GPUs will still be used for rendering, but in the AI market, assuming NPU companies do well, they'll gradually, little by little, increase their market share. And technically, that's the right direction for the architecture to go, actually.
Then from the perspective of video editing, it might even get better. Our GPU prices are actually really high.
That's right, too expensive right now.
So we can summarize the advantages of NPUs over GPUs as three main points. First, the initial adoption cost is much cheaper. Second, operating costs are also lower. And third, for specific algorithms, they are much more efficient. It's a trifecta. Since these are all AND conditions, meaning they're all good at once, it seems inevitable that NPUs will gradually replace GPUs.
I think that will be true in the AI domain, especially for inference. I believe this shift will happen quite quickly. In the training sector, highly complex software is still needed based on the QDay API. But interestingly, there are various rumors, and the most plausible one is that OpenAI doesn't use the QDay API when servicing ChatGPT. That means it's already transitioned. Especially in the inference market, NPUs will penetrate the market very rapidly because of GPT. However, for training, where significant software flexibility is required, I personally believe GPUs will maintain market dominance for some time.
When it comes to AI services, you mentioned that NPUs will be adopted much more widely, especially for inference. But I have another question. Previously, we'd celebrate breakthroughs from data center research, like when they differentiated cats from dogs, or when AlphaGo beat a human. Those were big moments. But ultimately, for us to truly use AI effectively in our daily lives, AI needs to run well at the edge, on devices themselves. We can't just stick a huge graphics card like a GPU into a laptop, can we? Can NPUs solve that problem?
It wouldn't be able to handle something like ChatGPT, but smaller models are possible. Even companies like Samsung or Apple have what's called an SoC, system on a chip, where various components, including a CPU, GPU, and NPU, are all on a single chip. This allows lighter models to run at the edge, and then heavier ones can be sent to a backbone server for computation. That's where things like 5G come into play, receiving data back. There are even hybrid approaches where specific layer operations are done at the edge, and heavier computations are sent to an edge server to be combined. Many ideas are being explored. Ultimately, whatever can be done at the edge should be done at the edge, and what needs to be sent to a data center should be handled there.
What you're talking about, often called a neural engine, means that while NPUs can't replace everything at the edge, they can certainly take over a lot of tasks as technology advances. Does that also mean the absolute quantity of hardware decreases significantly? With Nvidia, you need to set up a DGX system with 8 GPUs, each costing around $7,700. In the case of NPUs, if they deliver the same performance, can you use far fewer OHM?
That's right, if it's the same TOPS, tera operations per second, there's also something called effective TOPS. TOPS just refers to how many calculators are on a chip, but what's more important is the effective TOPS, how many are actually running. When a GPU is running at about 20 to 30% utilization, an NPU runs at 70 to 80%. Because of that, you can operate with a smaller chip size and fewer units. And then there's the issue of rack space in data centers. If you look at places that have A100S installed, you often see empty space above them. The real estate isn't being utilized.
It means the building has vacant space.
If you put in one A100, everything else has to sit idle. The racks above it are empty and only 2 or 3 A100S are running. With NPUs, you can plug in many more per unit of rack space because all of that itself is cost. If you're servicing the same traffic and 8 A100S are needed, then with NPUs, maybe only 4 are needed, and then you can fill the remaining 4 slots with more NPUs to bring in other traffic.
Then it's about operating costs and efficiency. With various LLMs emerging and a trend toward more specialized or vertical LLMs for specific services, are NPUs also becoming more vertical? Are they being tailored to specific algorithms, or are they still designed for broader use?
A more vertical approach for components is something every company wants to do. The teams attempting this full-stack AI, like KT and us, are making good attempts, but the closest to having truly made it is Tesla. Beyond Tesla, even Google, with its TPUs, hasn't been able to achieve such vertical AI. It's not about things operating separately. The AI service needs to be defined and the algorithm customized to fit that service. It's not just about grabbing a famous algorithm like GPT-3 because it's well known. You need to build the infrastructure to match the algorithm, fitting it to the service. It's not about just buying DGX with 4A100S or 8A100S. Even the data center's electrical infrastructure needs to be built to match the service and algorithm. Tesla is doing that. They're building their own data centers.
They're going full stack then?
The term full stack doesn't just mean gathering all the components. It means cross-optimization across each layer. It's like saying, this is what our hardware is like, so we'll change our algorithm to match. Algorithms are developed with the hardware in mind, and the hardware is designed to be friendly to your algorithms. Even the algorithms might say, your quantization goes this far, then I'll develop the algorithm to match that. And the algorithm developers will look at the service. So true full stack means understanding the information across all layers, both above and below, and performing cross-layer optimization. The only team on Earth that has implemented this so far is Tesla. Tesla uses Dojo for training, and the trained models are then used with their dedicated chips for autonomous driving. Dojo, being a training chip, runs in their data centers, which they build themselves. And for self-driving, they also have their inference chips. These small chips gather and send information. They truly have everything: service, infrastructure, hardware, and software. It's been more out. There's a Tesla YouTube video explaining the Dojo chip. If you watch it, they don't explain the hardware as hardware, they just casually present it as one of several software layers. Hardware is simply assumed to be there, designed to fit everything else. That's what full stack means in that context.
It's completely organic then. So there's Tesla's self-driving service, and the algorithms for it are developed to fit that. The Dojo chip is their data center chip, right? They make that data center chip to run those algorithms, and then the chip directly installed in the car seems to be the FSD chip, the full self-driving chip. They completely create that chip in an integrated, organic way.
That's an obsession for Elon Musk. I used to work at SpaceX, and with Starlink version 1, even though the volume wasn't huge, he heard, hey, if we make a dedicated chip, the performance will be better. So immediately, a dedicated chip. Elon Musk's obsession with silicon. That's what an engineer is. And honestly, that's the philosophy of someone who changes the world.
When you mention that obsession with silicon, Apple has been hugely expanding its lineup lately too. Is that similar?
That's right. Companies that are truly successful are different in some way. The teams that invest in silicon are ultimately the ones that dominate IT. That's true for Apple too. They acquired PA Semi when Steve Jobs was still around and have nurtured that team ever since. Their phones might be different because the silicon is different. They cross-optimize the silicon and the OS, tailoring their OS to the silicon. Now they're even making their own. They practically look at it. It's been a while now. The M1 was probably the first silicon to truly offer a different user experience. A team that invests in silicon is the real deal. When I talk about how KT is truly serious about AI, it's because KT invests in infrastructure.
I was actually curious about that. You've released a data center product with KT recently, the Atom series, right? But the Ion series was originally specialized for finance. Why did you move into data centers, especially since it seems like such a different area?
This is Rebellion's story, but before I founded the company, I was trading on Wall Street using FPGAs. To execute trades faster than with software for high-frequency trading or low-latency trading, FPGAs were quicker. However, as human history has shown, you always start with software, move to FPGAs, and eventually transition to ASICs. My initial theme for starting the company was to become a niche player in a market where latency is crucial by creating dedicated hardware. But as often happens when you start a company, you get a bit overconfident and aim for a bigger market. So initially we didn't directly target data centers. That's because there were already TPUs and various giants, so we decided not to enter a market that was big but fiercely competitive. However, during our seed and pre-Series A rounds, KT came in and we thought, if we have a strategic partner, this is a game we can play. Even though there are many impressive NPUs, Nvidia still holds a monopoly. From Nvidia's perspective, it's like all of us are the same company. It's become a situation where everyone is on equal footing because Nvidia is the only one doing it. What became important was, if Rebellions could secure data center references faster than others, then it would be a worthwhile game.
So you thought if I develop it myself and someone actually uses it, then it's worth a shot. Is that right?
A reference means something like, oh, the Rebellion's chip ran for a year without any issues at KT's IDC in Bundang. That's what's needed. If a data center can get these references faster than other NPU companies, they can become the #1 NPU provider. Ironically, it's Nvidia's GPU monopoly that created an opportunity for latecomers like us. KT was the team willing to help us seize that. Now, our live service is running at KT's IDC this first half of the year, and once we establish that reference, we can go global. We're aiming to build up our presence from being a niche player, little by little. And then, conveniently, ChatGPT came along. The tide is coming in. We're diligently rowing, truly targeting to be #1 globally. The results for Atom from MLPerf will be released on April 5th, US time. It's going to be a truly astonishing chip, world-class, with incredibly good latency. Please look forward to it on April 5th, US time. MLPerf also has various metrics, including inference and training.
It's a different category, right?
If you look at track and field, there's the 100 meter, the 400 meter hurdles, etc. Nevertheless, the highlight of track and field is the 100 meter dash. There's batch 1 latency or single stream, where you measure latency by putting in a single batch. For batch multi-stream or offline scenarios, the number scales up as the chip gets bigger. It's about bringing in and processing things simultaneously. But for single batch, like the 100 meter dash, it's not about stamina but explosiveness, and the NPU architecture really shines through. That's why companies like Google demand batch 1 latency. When we've been doing our sales lately, our numbers are obviously better than GPUs and even way better than existing NPUs. So please look forward to April 5th US time.
I'll be looking forward to it, and it would be great if we could introduce that news once it's released. So, how is Rebellions further preparing for the ChatGPT era? Are you going even more vertical on the hardware side or establishing a software system? What kind of preparations are you making?
First, chips need to keep getting bigger and memory specifications need to keep increasing. Hardware development usually has a pipeline of 2 years, and 2 years is actually incredibly tight if you go all the way to mass production. During those 2 years of hardware development and mass production, what we're realizing is that algorithms are just going to keep getting larger. Before, if you targeted one specific thing, that market would be sufficient and generate enough volume. You'd think, okay, we'll cover this generation with this, and the next generation will handle bigger models. Even GPUs have a typical silicon pipeline of about 2 years, but they actually swap them out every 3 years. GPUs have incredible aging, but right now, from the moment you architect the silicon to the point of mass production, we have no idea how bugger models will go. So we're trying to hit a moving target. Since the target keeps getting bigger and we don't know what the market will look like when our silicon comes out, the most crucial thing is scalability, even if it means sacrificing a little bit of something else. We need to be able to service any large model simultaneously by using multiple chips, multiple dies, multiple cards, or even multiple nodes and racks. That scalability is a key advantage for rebellions. I mentioned that ion is a subset of atom, but actually 8 ions essentially make up one atom. Scalability is rebellion's theme, first, second, and third. To achieve global recognition, we need this one thing. The rebellion's chip is truly scalable. Rebellions is preparing by attaching multiple atom chips, multiple cards with atom chips, and even multiple servers to be scalable. Why? Because we don't know how big models will get or where the sweet spot will be. Models might grow to a certain point, then suddenly 1 to 4 billion parameters is enough. Or for about 10 billion parameters, we can scale down a 175 billion parameter trained model and run it. There will be scenarios like that, and we're contemplating what a scalable design for those scenarios would look like. You could say we're in the process of finding the answer.
When you talk about attaching dies, was it Apple's Ultra chip recently where they just linked 2 dies together? Is it the same principle?
There's that concept, and also chiplets used when attaching HBM. Apple did a great job with that. You might ask, why cut it up and use pieces instead of just making it big from the start? Well, if the die itself gets too big, the yield drops exponentially. So while making a larger die would definitely win, the cost is crucial. For something like the M1 Ultra, they use chiplets to attach multiple dies and also incorporate high-end memory called HBM, all within a single chip. If the model size gets bigger, instead of attaching 4 chiplets within one chip, they attach 8.
Just keep expanding it by attaching more and more.
Because we don't know what kind of model will settle down in the future. Like now, our team's main concern has been to definitely consider a scalable chip.
So the speed is much faster than expected, and it seems like Moore's law when it comes to AI performance isn't just directly proportional, but rocketing upwards. Going back a bit, I'm curious. AI semiconductors, like neural engines, are already integrated into various SoCs at the edge, right? Their performance is obviously improving, but how far will that go? Will it reach a point where data centers become unnecessary?
Oh no, I don't think it will. Phones and edge devices still have extremely strict power requirements. They don't have fans like data centers do, and since you have to carry them around for at least half a day, the power consumption requirements are just too tight. In fact, they share all the available power among the CPU, OS, and the model.
And the screen needs power too.
That's right, compared to how fast models are growing, the gains from on-device processing will be too slow. So ultimately, most meaningful LLM-based tasks will likely be offloaded to data centers. That's probably the best way to understand it.
Yes, so for the foreseeable future, the NPU competition will continue to be focused on data centers. And in fact, communication networking technologies like 5G and then 6G might actually complement that by providing faster responses, since it's all about getting a quick response.
All companies are now flocking to LLMs, and we're also rowing hard while the tide is in. But actually, other AI domains are continuously emerging too. There are so many applications that could easily run at the edge. And even generative models, while not getting as much attention as LLMs lately, have some really cool capabilities. Like, look at my picture and make me smile more. Or, hey, give Park Sung-hyun thicker eyebrows. These generative models aren't quite there yet, but once semiconductor capacity at the edge increases, you could just do it on your phone, even if it's a bit slower because going fast would consume too much energy. What if it takes a minute to make me smile? For urgent things, you can send them via 5G or 6G to a data center for processing. So I personally think we'll see more edge applications for those kinds of generative models. But even then, people designing phones might say, too much power, let's send it to the server.